today's. Oh yeah, sorry. Let me start again. So welcome everyone to today's string seminar series, and we're very happy to start with Alessandro Mininno from Hamburg, and he's going to tell us about the asymptotic weak gravity conjecture and theory. Please.
Thank you for the introduction. It's a long time that I'm giving a talk here at a seminar series in string phenomenology, and today I will talk about my recent paper with Cesar, Timo, and Max on the asymptotic weak gravity conjecture and theory. So there is a weak gravity conjecture in the title. So of course there is the compulsory slide on the weak gravity conjecture. And then the idea is that every gauge theory coupled to gravity should have at least a particle that for which the Coulomb force is stronger than the gravitational force. And this has many shades. And the one that we will use in particular focus is the tower weak gravity conjecture, and then the expression of the weak gravity in terms of the repulsive force conjecture, that is say that the highest charge to mass ratio should be self-repulsive. And then you, to avoid to have bound states, and then you will have that the Coulomb force is larger than the gravitational force, and if there are scalar, also the Yukawa contribution. And the tower weak gravity, instead, the idea is that it's not only regarding one single particle, but you must have like a tower of states of super-extremal particle or states that should satisfy the gravity conjecture. And to verify the tower weak gravity conjecture, one must be able to compute the charge to mass ratio for these candidates of super-extremal states. And this has been done in the years in many setups where this charge to mass ratio is known, and this has been done for BPS particle in 4D n equal to 2 theory or 5D n equal 1 theories. Whenever you have a perturbative heterotic string dual, or in the weak coupling limit for the gauge theory in F theory compactifications. And however, the charge to mass ratio for non-BPS states instead is not so easily computed, that it can be calculated reliably only when it's, as I said, in the weak coupling limit. And this is when the coupling constant goes to 0, and we call this kind of weak gravity conjecture the asymptotic weak gravity conjecture. And this has been studied in the last years in 6D or 4D compactification by Timo and collaborators. And then the idea is that whenever you don't have BPS particle states, then you will find a non-BPS excitation that are available that gives you the tower that satisfies the weak gravity conjecture. And they exist, for instance, in 4D, in emergent string limits, where the BPS string dual to heterotic string becomes light. And this is actually a result that we explored last August, July, August, and in about 4D n equal 1 compactification of F theory. And these are cases in which there can be also the possibility that there are no particle-like excitation, that you can furnish the tower of super-extremal states. And this happens because what is important is also to compare the scale at which the weak gravity conjecture is supposed to be valid, and the scale of quantum gravity when gravity becomes strongly coupled. But now that we looked at the 4D case or the asymptotic weak gravity conjecture in general, there is a puzzle even in 5D case n equal 1 in which not all the direction in the charge lattice have a BPS tower. And because in the case in which there are a BPS tower, this has been explored in a paper by Alim, Ben, and Tom, but recently also by the Cornell group, and again, Ben and Tom, in which you can find that there is a tower of BPS states as soon as the curve associated to that BPS states it's in the movable cone, but in the direction in which there are no BPS tower, it remains open the problem of saying what is if the tower with gravity is satisfied. And this is what we did. We focused indeed in the role of super-extremal non-BPS tower that can give a complement tower in all the direction in which there is no BPS tower associated. But as I said before, in case of non-BPS object, then we needed to focus on weak coupling limits. And so our interest lies in those directions that are not populated by BPS tower, but for which you can realize a weak coupling limit. So what we did is to refine the classification of infinite distance limit to test the asymptotic weak gravity conjecture. We classify all the linear combination of U1 factors that can become weakly coupled in that limit. And the upshot of the talk that I will now summarize already is that only the U1 that are obtained from reducing the C3 form of M theory on a curve in the generic fiber or in a generic degenerate fiber, but at the finite distance degeneration, they are the only one that can become weakly coupled. But in this way, any direction in the charge lattice that is not populated by a tower weak gravity conjecture for which is a weakly coupled limit exists, then then we find a tower of non-BPS states. And then the claim is that either if there is not BPS tower of states, either there is no weak coupling limit, or if it exists, then the tower is replaced by super-extremal non-BPS states arising by excitation of the critical string, compatible with the emergent string conjecture. So the talk will proceed focusing on defining what is the weak coupling limit. And then I will show you what are the candidates for the non-BPS tower in this weak coupling limit. And then for some of them, I will show also that the weak gravity conjecture is, of course, satisfied. So we are M theory and on Calabi-Yau 3-4, as I said. So you compactify M theory, and that you find an effective action in 5 dimensions, in which you will have some scalar field that are this high that are a function of the Kähler moduli, VA, in the case in which the Morricone is simplicial. And then you have the FOA that are the field strength of the U1 factor associated with a given gauge coupling, F alpha beta. So if you want to consider a generic U1, this for a curve class C, this will be expanded in the basis of Morricone generators, and you will define the gauge coupling to be a linear combination of the inverse of this kinetic matrix with the given charge given by the linear combination of the U1. And what we want to say is that in the weak coupling limit, then we look at a certain excitation with a certain of associated to a particle of mass mk, and we require we check if satisfies the force weak gravity, the repulsive force conjecture in this formulation. And these are related with the form that I showed before, when you explicitly write down the Coulomb contribution, the gravitational, and the contribution from the Yukawa. Now, the point is that we need to define what is a weak coupling limit. And as I said at the beginning, when there is this, we need to define when we can consider the theory weak coupled, and then we take the scale at which the weak gravity conjecture is supposed to be satisfied, and then for a given U1, the given curve will be this factor here, and we ask that the ratio between this scale and the scale of quantum gravity goes to 0. So in this way, we are able to say that our weak gravity theory, our weakly coupled theory, is inside our EFT. And the claim that we have, that I stated confusedly before, is that in case you consider this M theory compactification, and in a given direction, you don't have a BPS tower of states that is satisfying the tower with gravity conjecture, then either there is no limit in the modular space in which for that combination of U1, you can realize a weak coupling limit, or there is a limit and the alternative tower that is replacing the BPS tower is given by non-BPS tower of states that is which is a part of the tower of excitation of a critical strings that is becoming light in this limit, and then it satisfies the self-repulsiveness asked by the repulsive force conjecture. But what this claim means? Well, this claim is can be reversed in a different way. Instead of looking to the direction that are not populated by BPS strings and check if there is a limit or alternative tower, coupling limits. Then for these weak coupling limits, either there exists already a BPS tower of states that it's satisfying the weak gravity conjecture in this for that direction, or there is a non-BPS tower of states that is associated to that we find to be associated exactly with the weak coupled critical string. So since this is a weak coupling statement, and we want to be sure that this is inside our EFT, it's sufficient to check if there is a combination for which this F alpha beta goes to 0. And you remember that this is the one entering in the definition of the cage coupling. And then you compute the scale of quantum gravity, the species scale of your theory, and check that this is a weak coupling limit. And since you can rescale your moduli so that the overall volume, you can keep it constant, it is sufficient to analyze the limits in the vector moduli space of MT. And this is actually very nice that that is possible because those kind of limits have been already studied before by Lee, Lerch, and Weigand. And there are two kind of limits for M-theory compactification on Calabi-Yau threefold. Either they are the limits of type T2, where the Calabi-Yau admits a torus vibration, and then the limits, remembering the parameter lambda that was rescaling the volume so that it remains finite, are acting on this way, on the T2 fiber that shrinks. And then, or the limit can be for those Calabi-Yau that admits a surface vibration that can be a K3 or a abelian surface. And in this case, they scale differently. Of course, they must be exclusive. Either you have a T2 or a K3. So in the case of the T2 limits, then the weakly coupled U1s that we find are those associated to the KK-U1 of the lift to F theory of the base of the Calabi-Yau threefold times S1. And the associated tower to this are BPS states, reflecting that, in fact, the generic T2 fiber is a movable curve. And this is consistent with what Alim, Ben, and Tom, also the recent paper, have found. In the case of K3 or abelian surfaces kind of limits, the situation is more complicated. But the idea is that you have this U1 and you reduce the C3 over a curve in the generic fiber, and then the U1 that are weakly coupled are either those indeed associated to the generic fiber, or curves containing the generic fiber arising at finite distance in the fiber moduli space. So we needed to study the different kind of degeneration that the fiber can have and check if such degeneration are at finite distance in the moduli space. And then the objects that are charged under these U1s can all be interpreted as excitation of the heterotic string obtained by wrapping M5 branes on this generic fiber. But let's be more specific in analyzing the BPS tower. And the idea is you go case by case. Let's go to the type 2, the T2 case limits, where you have the generic fiber, and this can be degenerating in a given locus of the base. And then you can write the generic elliptic fiber as a positive linear combination of the fibral curves. And this is also for in any point of this. And you analyze all the possible linear combination of U1s that can become weakly coupled. And the one that becomes weakly coupled is exactly for the generic one in which all the coefficients are positive and non-negative. And then you check that the ratio between the weak gravity conjecture scale and the species scale are satisfied. course, we checked also that all the other combinations are non-weakly coupled, and this is in the details in case in the future you are interested. But this kind of direction for the U1 is populated by BPS particles, and these are associated to wrapping. So these are obtained by M2 brane wrapping the generic fiber, and this is the KK tower of the effective 5-dimensional theory if you consider a 60-dimensional limit. And the BPS invariants are non-zero, and this is being confirmed also explicitly by the computation of the previous paper, but also by Noether-Lefschetz theory. And then you can find, then we have a tower for this case, which is the one given by BPS tower. In the case of the K3 limit, instead, what is important is to check where this weakly coupled, where is the curve that is we use to compute the weakly coupled U1. Then either the curve can be in the generic K3 fiber, or you look at the different way of degeneration of the Kulikov type. In the case in which the Kulikov, the degeneration of the Kulikov of type 1, then this is at finite distance in the K3 modular space, and this also defined for both of them. All the U1 are weakly coupled. And instead, in case the degeneration are of type 2 and type 3 that are generically at the infinite distance in modular space, then a very specific linear combination of U1 will give you a weakly coupled U1. Otherwise, generically, each of those U1 will be at infinite distance and non-weakly coupled. And now what is important is to check what are the states charged under this, and how can we justify that we find a tower for this. And to do this, we need a little bit of machinery to define the charge lattice, and in particular, we need to find the dual to the charge lattice of the polarization lattice of the K3 vibration, and then for which we need to check the different kind of curves that are giving you the weakly coupled U1. And there are different cases depending on what is the self-intersection of these curves in this lattice with respect within the K3 fiber. And we distinguished, we can split the lattice in two between those that have positive self-intersection or negative one. And the idea is that in case the self-intersection is non-negative, again, we can find a very precise tower, and this is given by BPS states. And the reason is that all these curves are movable, and then by being immovable, then by also the results of the previous paper by Lee et al., and there will be a tower of BPS states given by M2 brane wrapped on this sigma. And then you have a BPS particle satisfying the weak gravity conjecture. But in case in which the self-intersection is negative, this is not movable anymore, instead it's rigid, and then this ray doesn't support the BPS tower generic. And then what you would want to do, since you know that you can realize a weak coupling limit for this direction anyway, for the discussion, as we have said before, because the K3 fiber is not degenerating or the degeneration is at finite distance, you need to look for other objects that satisfy the tower weak gravity conjecture. And the non-BPS states are given by the excitation of the emergent string that becomes light in this limit. Now, to argue for that, we used well, in the case in which the charges are only belonging to the negative lattice, then we identified those non-BPS states with the excitation of a 5-dimensional heterotic string obtained by wrapping M5 ray on the K3 fiber. And the reason why there are non-zero states for this object is that we identified this the given left excitation with the certain Donaldson-Thomas invariants obtained by compactifying the M theory on another circle. And this fact that these states exist is because we can relate the Noether-Lefschetz number that are non-zero with being non-zero also the Donaldson-Thomas invariant of the D4, D2, D0 bound states. And then there exists a distinguished set of non-BPS states that have a very specific left-moving excitation that is given by this combination here, where Nij is the inverse of the intersection formula of K3 fiber. And this relation is actually really important because one can show that by explicitly computation of the weak gravity conjecture, that if you consider an object with a given mass and m squared, and then this is his mass, and you will have two possible contributions. One is the usual mass proportional to the tension, then the volume of the cycle of the divisor wrapped by the M5 brane, and then you will have a mass a contribution to the mass coming from the moving from the Coulomb branch, and plugging this expression inside the repulsive force conjecture, you will see that you have the usual BPS condition that gives you the right and left hand side of the repulsive force conjecture to be equal. Then this non-trivial contribution coming from the presence of moving in the Coulomb branch, which is ubiquitous in this kind of theory, will give you the same contribution on the left and the right hand side. So it's like a shift from the extremality of the black hole associated to this kind of particle. But on the right hand side, there is this extra contribution here. But this extra contribution here is actually zero as soon as we impose that the left moving excitation of the string are exactly of this side, because this contribution will give you a -1. So at the end, the repulsive force conjecture is satisfying, and these are the tower of non-BPS states that are necessary in the case in which we don't have a BPS tower. So now I can conclude, because I think that I am almost done. And the idea is that we classified all the linear combination of U1 factors that becomes weakly coupled in this limit. And as I said at the beginning, you have either the U1 that can only become weakly coupled when you reduce the C3, either on a curve that is in the generic fiber, or on a curve that is, yes, in the degenerate fiber, but at finite distance in the degeneration of moduli space. And in this way, any direction in the charge lattice that is also non-populated by a BPS tower can either then either there is no weak coupling limit for that U1, or if there is, then there exists a super-extremal non-BPS states that are associated to excitation of the critical string that satisfy the tower weak gravity conjecture. And as I said in the paper, as I said before, what we showed is exactly like this. We classified the weak coupling limit, and we checked what kind of tower are associated for each weak coupling limit. Of course, in this talk, I needed to simplify a little bit the discussion, and then I focus on the torus type and K3 with a specific choice of the lattice, but all the other cases are in the paper. And the fact that we have another confirmation that the asymptotic tower weak gravity is there is the satisfaction of the saturation of the asymptotic tower weak gravity conjecture also for this case, as we did for the case. Then I think that this is another way of saying that this is well, it's supposed to be true in all the cases. So I think that I will stop here, and I will thank you very much.
Okay, thank you, Alessandro, for the talk. Are there questions? So maybe before while others may think of a question, so can you briefly give an intuition for these U1s for which you cannot take a weak coupling limit? So is it basically directions in the Kähler moduli space where
well, you can
somehow
have
you cannot blow up the cycle?
for those cases in which so there are different cases. Either you have you have a decompactification limit. So the idea is that those who, in that case, you will say that the weak gravity conjecture looks to be weakly coupled, but when you compare it with the scale of quantum gravity, you are actually above or at the same scale. So you are actually decompactifying, and then it doesn't make much sense maybe to ask if the weak gravity conjecture is satisfied in that case. Or in the case in which the degeneration of the Kähler fiber are at infinite distance, then in those cases we don't know what to say about those U1. It's a very weird. It's different situation. We don't know. There is a lacking of the tau, but we cannot say much about the weak gravity. The idea is always like this. The idea is that when you compare it with the species scale, you will find that it's above. And so I guess that it's the usual interpretation is that simply it is not a symmetry of the effective field theory in 5D, but it's more it's better to consider the compactified theory. Yes.
Okay, Marcus.
Yeah, thanks. So I quickly wanted to ask, maybe I missed it during the talk, but can you comment a little bit on tower versus lattice? So do you find a full lattice of states, or let's say a sublattice or something like charge quantization, or are there gaps in the lattice that sometimes appears in these compactifications?
So let's see. For sure, in the case of the BPS, in case you have a BPS tower, I guess that there is no that you set. Okay, recently they showed that in the other paper by the Cornell group, they found that both the tower but the sublattice, also the sublattice conjecture is satisfied. In the case of a non-BPS tower, as soon as you assume that the states are of this kind, I won't say that. I think that I cannot say much on sublattice. Maybe some of my collaborators can say something more, but I don't know. I think we checked the tower, but I don't know about the sublattice.
Okay, thanks.
Yeah, in the case of the K3 vibration, you can actually state that the polarization lattice is the one corresponding for the weak gravity conjecture.
Sorry, that was hard to understand. So you're saying that you find a lattice version of the weak gravity conjecture?
I'm just saying that you can actually show that the sublattice weak gravity conjecture is satisfied, and the sublattice is the polarization lattice of the K3 vibration.
Okay, thank you.
Thank you, Cesar. Actually, I forgot about this.
Okay. Are there any other questions? Yeah, okay. If not, then let's thank Alessandro again.
Thank you.
And we move on to Alberto.